All right, let's talk about these collisions now. We've talked about the cars running into each other, so let's talk about it. And if we're talking about it in terms of no external forces, the momentum before equals the momentum after. Okay, so momentum before equals momentum after. We're going to use that to calculate things, so we need to understand that. So here's our equation, well, basic thing. Net momentum before the collision, whatever that was, 2, 3 objects, whatever, it's going to be the same as after the collision that we have. So think about billiard balls. They run into each other. The first one comes to rest, the second one moves. Now, it would keep going if there weren't friction between the ball and the pool table. That ball would keep going. But when it hits the one, that momentum of that one ball is transferred to the other one. Just like the idea at the beginning of this with what they call Newton's cradle, the balls that bounce back and forth. They are collisions, and the momentum is transferred through those balls to the other one. If they are perfectly, they say if they're not permanently deformed and they don't generate heat, we have what we call an elastic collision. Anytime that there's anything else, it wouldn't be perfectly elastic. And for us, we don't see very many perfectly elastic collisions very often. But that's what we consider to be an elastic collision. So here we have an example. Before the collision, the ball is moving. The red one's moving, hits the white one. After the collision, or here's the collision. After the collision, the white one moves. Now, assuming that these are billiard balls, I think the guy's all mixed up because he probably should have been shooting the white one instead of hitting the red one and shooting the one out, whatever. All right, now if they're running into each other, okay, going this way, they both have momentum. This one has momentum to the right, this one to the left, and they hit, and guess what? They bounce. I mean, we all know this. They're going to bounce off and go the other way. Or if they're both rolling the same way, but the red one's going faster, when they hit, now the red one is going to go slower, and the white one's going to go faster. And you've seen all of these things. I mean, you've all experienced this in your life. You just haven't really thought about it probably in terms of momentum. But in all of these cases, if there were no friction, every single one of these, if these balls are exactly the same mass, they would transfer that velocity exactly to the other one. So like in this example here, let's say that this one was going 4 and this one's going 2. When they hit, this one will now be going 2 and this one will be going 4. That would be, in a perfect world with no friction, and everything is a perfectly elastic collision. So elastic, just understand this, elastic means they're going to bounce. Things are going to bounce off, they're not going to stick together. Inelastic collisions are, it says where they become distorted, they generate heat, it's an inelastic collision. Inelastic collisions usually we think of as the objects are going to stay together a lot of times. I mean, that's in here, that's kind of what will work, is when they collide, but they would stay together. Like two cars that crash into each other and become tangled, that would be an inelastic collision. Or in this example, we've got two train cars. One's sitting still, the other one's moving. So it's moving this way. They hit, they lock, and now they move together. Okay? So this is known as an inelastic collision. So assuming these are the same mass, this one's going and starting at 4, this one's at 0. They hit, now they're both moving at 2 when we're done. That would be true if they had the same mass before they started. Because we know the momentum before is going to equal the momentum after. Okay, so here's what we're talking about. The mass, let's say whatever that is, and we'll call it M, was 4. The mass of the other one was same mass. These were the same. Whether that was, 1,000 kilograms, whatever, doesn't matter. But this one wasn't moving. So the original mass was, or the original, what do I want to say? The original momentum would have been 4m. This would have been 0. So this would have just be 4m. Now afterwards, we've got 2 of the masses, so it's twice as heavy as it used to be. We now have a new velocity. Well, 2m times v, what's v going to be? What number put in here give me 4? Well, obviously 2. Okay. So twice as much mass is moving after the collision, so the velocity must be half of what it was before. The initial momentum is shared by both cars without loss. There's still conservation of momentum. Whether they're elastic or inelastic collisions, doesn't matter. They're always conservation of momentum. So we talked about this. There are external forces that we have to take into account. You know, if the billiard balls, they would have friction with the table and with the air. So they would eventually stop when they do. But, you know, originally that impact, when they impact, the one stops, the cue ball stops, and the other one keeps moving. Trucks, you know, eventually they're going to have friction with the pavement and eventually stop. If we have two space vehicles, so we have an accident out in space, they run into each other, or they dock, you know. But I like the idea of them running into each other, having an accident in space. That would be more exciting. They would keep moving. The only force affecting them would then be gravity. But if they were to lock together, in this example of the docking, the momentum would be the same after that it was before. Always stays the same. Now, anytime that there's any heat, anytime that there's anytime that we have anything like that, they would no longer be perfectly elastic. Technically, anytime that you can hear it bounce, it's not going to be perfectly elastic either. So at the microscopic level, we would see these, but we don't see them in everyday life perfectly. But, you know, electrons and things like that, those are perfectly elastic. So they would take place there. We can come close on an air track. We can come pretty close to creating some pretty good frictionless surfaces, and we get some pretty good examples of elastic and inelastic collisions that we can use there. All right, so let's think about this. One glider is loaded so that it has 3 times the mass of another glider. The loaded glider is initially at rest. The unloaded glider collides with the loaded glider, and the 2 gliders stick together. Describe the motion of the gliders after the collision. What's going to happen to them after? Oh, lost it. Well, the mass is now 4 times as big. So if the mass is 4 times as big, then the velocity would have to be 1/4 as much as what it was before. Or here we go. How about this? Consider a 6-kilogram fish that swims toward and swallows a 2-kilogram fish that's at rest. So here he is, swimming along. This guy's not moving. He's going to have some lunch. Okay? So he's 6 kilograms, and he's moving, what is he, 1 meter per second. Now swallows the little fish. What's his velocity immediately after he eats the fish? Well, remember, law of conservation takes place, and we're not going to worry about water resistance in this example. Okay, well, here's my stuff. Okay, momentum before, momentum after. So what was his momentum before? Well, he was 6 kilograms. He was moving 1 meter. The guy was 2. The other one was 2, but not moving, so that's 0. So 6. Afterwards, they now are 8 kilograms with the velocity, what we're trying to find out. So it's 6 equals 8v, you know, v equals 6 over 8, or 3/4. So 3/4 meters per second. He's going to lose a little bit of speed after he eats his lunch. All right, what if he were moving at 2 meters per second? See if you can calculate this one. Stop the video, figure out what his momentum, or what his velocity would be after he eats lunch. All right, hopefully you figured that out. It would be -2, Oh, what is it? Okay, I'm not reading this very well. They're saying the fish is moving 2 meters per second. So if this big fish is going this way at 1 meter per second, the other fish is going this way, we're going to say that that's negative because they're opposite. It's opposite direction. So one has to be going one has to be positive, one has to be negative. So that we just have to define that. We don't really care which one, but we have to define one of them as being positive and one being negative. So let's work through this example now. Okay, so here it is, 6. Now here it's 2 at -2. So therefore, he's going, or his momentum is 2. 6, -4, 2. Still have the 8 when they're together. Now take and divide. 2 equals 8v. Divide by 8. And we end up with 1/4 meter per second. All right, what if the fish were swimming at -3? Think about that one. It's -3 meters per second. Well, then they would both have equal but opposite momenta, which, by the way, is a plural of momentum. Therefore, as soon as he got done eating, he would be stopped. He wouldn't be moving. All right, so if we goes at -4, if the big fish or the small fish is swimming at -4, so he's going really fast now, 4 times faster than the big one. Why he wasn't swimming away from the big one, I don't know. But decides to swim into the big one's mouth, and we would end up going, the opposite direction when we're all done. 6, here, this would be 6, this would be -8, overall -2. -2 equals 8v, so -1/4 for his velocity. And since we talked about momentum, we said they are vectors, so therefore we can start to do some things with vectors. So even if they're not on a straight line, everything up to now has been a straight line, but we can now do things that aren't on a straight line. So let's say these two cars meet, they're not going in a straight line. They're going this one's going that way. That's not a very good line. This one's going this way, this guy's going this way, and they run into each other right here. And they hit, and they move. Well, what's going to happen? Well, we know they're going to move off in that direction. Well, this is still vector addition. Whatever this momentum was here, whatever that momentum was here, drew our parallelogram. My overall momentum is the combination, the addition of those, the vector addition of those two things. Okay. In this case, if they were exactly the same, the overall momentum would be, 1.4 times greater than what that particular one, or what either one of them had before. Or how about this? Here's this firecracker. It's falling down. And where did my firecracker go? Okay, firecracker falling down, and then it explodes right there. Okay, I'm having problems with my smartboard, but other than that, I'm okay. The momentum of the fragments prior to exploding and the momentum of the fragments after exploding is exactly the same. They are the same as what they were, before. And I really wanted to kind of draw this out here a little bit better. So let's go back. All right, so here it is. He's falling down. This is his momentum of the firecracker falling down. Now the firecracker explodes. That, even though you might think, oh man, there's all this other, yeah, there is all this other stuff, but guess what? Whatever happened, it's still the same. The momentum of that, because it was all part of the system before, there was no additional force added to it, nothing additional added to the firecracker. Then even though this part's going out that way and that part's going out that way, if you add those vectors together, you end up with the same thing that you had up here. Because momentum has to be conserved. Now that one seems a little bit hard, so think about it just a little bit, because that is the way it is. It's going to, whatever there was when it was falling before it exploded, that's the system. The momentum is still the exact same thing after it explodes. All right. Now, momentum's even conserved for elementary particles like protons, neutrons, electrons, and so on. And this shows things in the bubble chamber, and I really have no idea how this is supposed to show me momentum is conserved. But it looks cool.